we have defined the assuming the n-1 dimensional change of variable formula. We have defined the surface integral here. The x is a parametrization of our surface. Okay. Now, before going further, we consider some we consider some example. Consider an example. Example. If S is the graph of a function, S is the graph of a n-1 variable function. Maybe not x. Here U is n-1 dimensional region, and phi is a function, continuously differentiable function over U. Then what's this? Then our xu is u phi u. That is xi equal to ui for I from 1 to n, and xn is phi u. Okay. Now what's the n? What's the n? N is the Jacobian determinant of x which is respect to u. Okay, so what's this n? The last component is easy because xi is ui for I from 1 to n minus 1. Okay, so from this we see that the last Jacobian determinant is 1. This is 1. This is easy, but the other, as an example, we compute the first one. The first one, we need to compute this determinant. x2 to u1, x2 to u3, u2, x2 to u3, x2 to un minus 1, then x3 to u1, x3 to u2, x3 to u3, x3 to un minus 1, then xn to u1, xn to u2, xn to u3, xn to un minus 1. What's this? This is x2 to u1. x2 to u1 is 0. x2 to u2 is 1. x2 to u3 is also 0. The other are all 0. Then x3 to u1 is 0. x3 to u2 is also 0. x3 to u3 is 1 again, and the other are all 0. Finally, xn to u1, xn is phi u. Okay, xnu is phi u. Therefore, xn to u1 is the first derivative of phi. xn to u2 is the second derivative of phi, and xn to u3 is the third, and finally we obtained this result. This is a matrix of this form: 0, 0, 1, 0, 1, 0, 1. The last row is D1 phi, D2 phi, Dn minus 2 phi, Dn minus 1 phi. This is the matrix. So the determinant of this matrix, how to compute this? We can move the last column to the first column. When you move this last column to the first column, this matrix becomes a matrix of this form. Become a matrix of this form. It will become a matrix of this form. This is D1 phi, then this is 1, the other are 1, then all these are 0, then this is D2 phi, Dn minus 1 phi. Become a matrix, other elements are all 0. So the determinant of the new matrix is D1 phi. Okay, because the other diagonal elements are all 1. Okay, so the determinant we want to compute is almost the derivative of phi, which is respect to u1. But you move the last row to the first row, you need to switch the two rows one by one. Then how many rows do you switch? Because this is an n minus 1. This is a matrix of order n minus 1. So before this row, there are n minus 2 rows in front of it. So you need to have a minus 1 n minus 2 d1 phi. So the determinant of this is minus 1 n minus 2 d1 phi. This is the result. This is the first component. Okay, so I will move to next page. So n is the first component is minus 1 n minus 2 d1 phi. Similarly, you can compute the second component. It is also minus 1 n minus 2 d1 phi. Finally, minus 1 n minus 2 dn minus 1 phi. The last one is here. We already know the last one. The last one is given here. The Jacobian determinant is 1, but we have a minus 1 n plus 1 here. So the last component of this n, is minus 1 n plus 1. So this is our n. And we want to write this n in a more convenient form. We can write this by minus 1 n plus 1. Then minus d1 phi minus d2 phi, this is 2, minus dn minus 1 phi, then the last component is 1. So this is our n. That is when our surface S is the graph of a function, we have computed the normal vector capital N. Therefore, the surface integral, the norm of n is square root of 1 plus the gradient of phi square. This is the norm of this vector n. Okay, the norm of n is the square of all the components and sum up, and then take a square root. So this is the square root of 1 plus the gradient of phi square. So for the function f defined over the surface, this should be u f xu. What's xu? Xu here, xu is u phi u. Okay, this is the parametrization, the expression of the parametrization. Have you seen? This is the expression of the parametrization. So fxu is fu phi u. So we have fu phi u, and then the norm of the normal vector, that is square root of 1 plus phi square, then du. So this is the special case of higher dimensional surface integral. Okay. This is also a generalization of our previous result about surface integral for a graph of a two-variable surface recorded in R3. If S is the graph of z equal to gxy, then we know that the surface integral of fxyz d sigma is here xy belongs to some two-dimensional domain. Then this is fxy gxy, and then square root of 1 plus gx square plus gy square dx dy. Okay, so compare our general case with the two-dimensional or three-dimensional case. We see that the xy is our u. Xy is precisely u. And the gxy is our phi u. And our gradient, the norm of the gradient of phi is exactly the gx square plus gy square. That is the gradient of g square. Okay, so this formula is also the direct generalization of the case we studied before. Okay, so we have no surface integral. And now surface integral, we only consider up to now we only consider smooth surface. Okay, but sometimes we need to study piecewise smooth surface. So S is piecewise smooth. What's piecewise smooth surface? For example, the boundary of a cube. This is a piecewise smooth surface. And the boundary of a cylinder. This is also a piecewise smooth surface. So piecewise smooth surface is the union of finitely many surfaces. So for the cube, we have 6 surfaces: S1, S2, S3. Altogether, we have 6 flat surfaces. Each such flat surface is a square. Okay, so the boundary of the cube consists of 6 squares. All the squares are actually smooth surface, but they are flat. Okay, and for the cylinder, the boundary of this cylinder has 3 parts. The first part is here, the bottom and the top and the bottom and the curved part. So there are 3 parts. 1, 2, 3. Okay, so this is also a piecewise smooth surface. So this is the concept of a piecewise smooth surface. Now, if f is a function defined on a piecewise smooth surface, continuous. So what's the surface integral of f over this piecewise smooth surface? Of course, we defined to be the sum of the integral over all the smooth surface. Here Si are smooth surface. Okay. So this generalized our definition of surface integral. Of course, if the surface intersect, for example, this is S1, this is F2, this is also okay. We allow to have some neglectable intersection, but this one is not okay. So this is S1, this is S2. Such intersection is not okay because they overlap very considerable. Okay, but in the case on the figure on the right, they only intersect at the point or in a line. That is okay. That does not affect the integral. Okay, so for piecewise smooth surface, we need to have some restriction on the relative position of all these surfaces. Okay,